I will now talk about the other operation that could change the structure, would change the structure of the tree, and we need to be careful about making sure that we maintain the binary search tree property. Okay, so the second operation is deletion from the tree. So if we think about, delete, okay, or binary search tree delete from tree T, and I have a pointer to node Z, okay? So I have now pointer to node Z and I want to delete it. Okay, so if I have a tree like this, I'm not searching for the nodes. Someone has given it to me. For example, someone says here is Z, remove Z from this tree. Okay, now I cannot just delete it because then I broke the tree now, and we need to structure it back such that, again, or to glue it back such that the binary search tree property is maintained. So deletion from a binary search tree has, we have to be careful a little bit more than insertion. Insertion, we just went all the way to a leaf and added that key either as a left child or a right child of that leaf. When we are doing deletion, we have now to think about a few cases. It's nothing complicated, but we have to think about them carefully. So let's look at case one. Case one here, where suppose we have a node here, let's say they call it W, okay, and this is Z here. So we have node Z, and imagine that Z doesn't have a left child. It has a right child here. Let's actually label it R, and that R has whatever left and right subtrees. Okay, they could be nil, they could be subtrees, and so on. And again, we want to delete Z. If we want to delete Z, now, if you think about it, actually, let me just fix the drawing a little bit, and so that to make sure it looks like it's a right or left child. Let's imagine that this is W, and Z is a left child of W. So if we want to delete Z, notice that everything in here, the keys here are all smaller than W. So I don't need to worry about W. I just need to make sure that things within this blue circle or shape, they still maintain the binary search tree property. So if I delete Z and Z doesn't have a left child, all I need to do is this. So I can now, W is still here. I can just replace Z by R, and R with its two children. Okay, so if this was A and this is B, A is a subtree, B is a subtree, this is A and B. Notice that the binary search tree property is maintained. All the keys in R and A and B are smaller than W, so everything is fine. All the keys in A are smaller than the keys in R. All the keys in B are smaller than the keys in R, greater than the keys in R, because that's what we had in the original tree. So this fix is trivial. So what does that mean? I make the parent of R to be W. I make the left subchild of W to be R, and we are done. This is all we really need to do. Okay, so in some sense we did W left is now equal R, and R parent equal W, and then you can delete Z and you are done. Okay, so this case is very simple. Now if Z was, again, and here again, one important assumption is that we have, I should not talk about this. Well, the important thing here I'm talking about is this, that Z doesn't have a left child in this case, okay? So it has one child, exactly one child. And if that child was a left child, it's nothing harder. So if I look at the second case here, but we have W here and we have Z, but Z has a left subchild, but doesn't have right subchild. And again, we have here A and B. The same story. If we want to remove Z, all I need to do is just make L as the left subchild of W. So now I can go to, this is W, and W goes to L, and L still has A and B as its two children. And everything is fine because the keys in L and A and B were smaller than the key of W, so we are set. And the keys of A are smaller than or equal to the keys of L in the original tree and in the new tree. The keys in B were greater than or equal to the key in L in the original and in the new tree, so absolutely no problem here. So these are the two cases where we are trying to delete Z Z has exactly one child. Of course, if Z has no children, it's trivial. You just remove it and you are done. You are not going to be violating anything. Okay? And I did not even discuss that case. Now, if Z has one child, these are the two possibilities. Let's look at the case now. The third case is when Z has two children. Okay, so let's think about this is W, and it has Z here, and Z has left, and it has right. Okay, and let's think about one simple case here that I'm looking at this kind of case here, and R is, let's consider R is the successor okay, let's delete this, is the successor of Z. What does that mean? What does it mean to be the successor? The successor is the smallest key that is greater than or equal to the key of Z. Okay, so if you look at the key of Z and you look at the right subtree of Z, all the keys there are going to be larger than Z, the key in Z, larger than or equal to the key in Z. If you find the smallest of them, this will be the successor. So if you think about Z and R is the successor, if R is the successor, the left child of R must be nil. Because if there is some child or left child of R, then R cannot be the successor of Z, because that left child of R is smaller than R and greater than or equal to Z. So that node should be the successor, and R cannot be the successor. Okay, so if we think about R being the successor, so the number that comes after Z, the number comes immediately after Z in the sort. If I think about the elements of the binary search tree as sorted, and I print them in sorted order, the key of R will appear after the key of Z. If this is the case, all we need to do is replace Z by R, and we are done. So in this case here, if I have, let's say here we have, node X, and it has its two children, all we need to do here now is replace Z by R, and we have left here, and R, nothing changes about it. Now we can keep X as its right subchild. Okay, so if you think about this, what happened here, again, we deleted Z and we put R in its place. Now let's look at the keys in the new tree that we formed. Do they satisfy the binary search tree? If you think about the keys in L, they are smaller than the keys in R. Why? It's smaller than or equal, because in the original tree, the keys of L, if you think about the keys of L, of nodes in L, the key in L is smaller than or equal to the key in Z. So L dot key is smaller than or equal to Z dot key. But we also know that Z dot key is smaller than or equal to R dot key. Okay, so we know that the key of L is smaller than or equal to key of R. We are set. The key of X is greater than or equal to key of R, because that's what we had in the original tree. So we did not change anything, right? So if we look at this tree here, the keys in R, L, X, and all their subtrees are smaller than the key of W. We are fine with that. And the key of L is smaller than or equal to the key of R. The key of X greater than or equal to the key of R. Therefore, the tree we have is fine. Now, this is a special case where really R was the successor of Z. What happens if R is not the successor of Z? So this is the last case here. If R is not the successor of Z, then we have, what did I call the parent? W. Okay, so now we have the last case. We have case 4. We have W here. We have Z. And Z has the left child. Z has the right child. And the right child could have anything here. Now the right child has to have left. The right child, this R, has to have left. Because if R doesn't have left, then R is the successor of Z. Think about it and make sure you are convinced of that. If R doesn't have left child, then R must be the successor of Z. So since we are talking about a case where R is not the successor of Z, then R must have some subtree, And in that subtree, somewhere else, the leftmost node here, y, which doesn't have left child, and this y could have anything here, x. Y is the successor, okay? So the successor is somewhere in the left of R, and it is the leftmost node. So keep going from R to the left child, to the left grandchild, to the left, and so on, all the way to get to a node whose left is nil. That will be the successor of Z in that subtree. So if we have this kind of case here, all we need to do, since we are deleting Z, we can make Y. We make Y replace Z. So now Y is here. So this successor will replace Z. And the left is still the left of Z. The right now is what was the right of Z, the R. And from there, we can now replace Y by X. So now Y becomes X, and X has its children. So if this was A, this was B, and let's say there was subtree here, C, then this is C, and this is A, and this is B. Okay, so what I'm saying here is that you want to delete this node Z. We want to delete Z. You look at R, you look at its right child. Right child is not its successor, so you come to the right child and you keep going left till you get to Y. This is the successor. Once you get to that, now you take Y and replace Z by Y. Now you make R as the right subchild of Y, and X replaces Y. Now let's look at the binary search tree property. Is it violated now? The keys of L are smaller than the key of Y. Why? Because if you look at the tree on the left here, the key of L is smaller than or equal to the key of Z. Z is smaller than or equal to all the keys on the right, including the key of Y. So we know from the left tree, the original tree, L dot key smaller than or equal to Z dot key. Z dot key smaller than or equal to Y dot key. Therefore, the key of L smaller than or equal to the key of Y, and we are fine there. R, in the original tree, Y was in the left subtree of R, which means the key of Y is smaller than the key of R. And this is fine here. So the key of Y is smaller than or equal to, the key of Y smaller than or equal to the key of R. So we are fine with this. C, the subtree C was on the right of R, and it is on the right of R in the new tree, no problem. If you look at X, X was on the left subtree of R in the original tree. It is on the left subtree of R in the new tree. A and B have not changed. They are still with respect to X in the same way. Therefore, this new tree satisfies the binary search tree property. We have not violated anything in this case. Okay, so this is how deletion works. Now, notice that the change that we make is in some sense local. I did not change the tree all over the place. Y replaced Z, and X replaced Y. This is all we are doing here. So it's really two changes. Now, what's the running time of this algorithm? Again, if you think about it carefully, for us to be able to do this, the first two cases here, if I go back and I look at the first two cases, when Z has only one child, it is O of 1 operation. We are just taking that child and replacing Z by it. So this is here O of 1. The second case where again Z has the left child only, it is O of 1. If we look at this case here and the right, Z has two children, left and right, but the right is the successor of Z, then it is O of 1. We just really replace the pointers of R and W. This one, the fourth case here, is more than O of 1 because when the right child of Z is not its successor, we have to look for the successor. Now, how long does it take to look for the successor? This case could be O of H, the height of the tree, because in the worst case, we might have to track a path that has that length. Okay, so if for example, to illustrate that, imagine that I have a tree like this. and suppose here we have 5 and 1 and 9 and 6, and this one here is 100, and here it's 90 and 80 and 70 and 60. And imagine that I want to delete 9. To delete 9, I need to find its successor. So its successor, I need to come here and go all the way to find. The successor of 9 is 60. So to find this, again, in this case, with the tree has a long chain, it will be governed by the height of the tree. Okay, so in the worst case, the running time of deleting from a tree, from a binary search tree, can take O of H. So to wrap it up, when we talk about binary search trees, we talked about like traversal, for example, traversal of the tree, where we want to print all the nodes of the tree. For example, this is O of n, in order, pre-order, post-order, and so on. Then we talked about searching for an element in the tree. We said this takes on the order of h, the height of the tree. Then we looked also at insertion and deletion. So if we looked at insert and we looked at delete, each of them also took O of h. Okay, so for this one here, we cannot really do much for the traversal, because no matter what the shape of the tree is, we have to visit all the nodes in it. Whether it's a chain, whether it is balanced, it doesn't matter. But what about these ones here? Again, as I mentioned before, we prefer something like this to something like this. Okay, so these are two binary search trees, both of which have seven nodes in them. And I can put here, for example, 1, 2, these are the keys, 1, 2, 3, 4, 5, 6, 7. And here would be 1, 2, 3, 4, 5, 6, 7. If I am searching for 7, here is going to take on the order of n. Here is going to take on the order of log n. Okay, so in a binary search tree, since these operations, search, insert, delete, and so on, are governed by the height of the tree, and there are many other operations that are governed by the height of the tree, one important goal for us is, can we enforce or put some conditions or constraints on the tree shape to make this h on the order of log of n? Okay, we cannot do much better. We cannot turn h into O of 1, of course, right? Because we have to fit all the nodes in the tree. So the smallest possible value of h can be on the order of log n. The largest possible value is on the is n itself, in the order of n itself. So we would like for the tree to have h on the order of log of n, so that these operations, search and insert and delete, in that case, all these operations now take O of log n. Okay, but for that, we have now to go beyond the basic binary search trees, and we have to talk about tree structures that ensure that the height is on the order of log of n, even when we insert and even when we delete. So now it's not just about maintaining the property that the keys on the left are smaller than the keys of the node, and the node key is smaller than the keys on the right. We also need to maintain the property that the height is on the order of log of n. And again, this is where we are going to go next, to a different type of binary search trees.